Greetings and welcome back. We're in the midst of now shifting our focus and dynamics from the means to the entire distributions. And thus far, we've exploited the chemical master equation approach for thinking about diffusion problems. And then after that, we looked at transcriptional problems, both for the constitutive promoter and then for the rather technical example of the two-state promoter. And now what we're going to do is we're going to shift gears entirely in order to look at a different class of physical problems which have to do with the control of filamentous structures in the cell. And the reason I think this is important is that one of the hallmarks of an approach or of a principle that is sort of deep is that it's far-reaching. And when I say far-reaching, I mean that it exhibits itself in quite different circumstances. So what we're going to do is we're going to revisit this experiment from Joe Howard and his group, but this time instead of asking about the average length as a function of time, we're going to be more demanding and ask what is the distribution of lengths if we do this experiment a bunch of different times. In other words, there's going to be a mean, but then there will also be a distribution about that mean, and what I'm going to claim is that the chemical master equation gives us an opportunity to try to reason about that. So in terms of the theme of closing the loop, this is one of these examples that's a bit in the figure 1 mode, although for all I know there may be the data on someone's computer somewhere. But what I mean by that is that although, as you saw, there were several features of this data, it shrinks, the microtubule shrinks as a function of time. This graph tells us that the number of motors on the filament is an increasing function, the linear function of distance along the filament, and this is the real data over here on the right, which we reasoned out in the lecture on rate equations, sort of by thinking about the mass balance, which is right here, you'll recall. And so you can go revisit that if you like. What we're going to do now is we're going to attempt, as I said, to use the chemical master equation approach for thinking about these cytoskeleton problems. So I guess I want to just note that, just like there was a continuum theory protocol, here we have a protocol that permits us to write down the probability distribution for the lengths. So I'm going to just go through this quickly. So as you can see over here on the left, the first element is that we want to consider our population of interest as a probability distribution. And what I mean by that is that just like we said in the case of the mRNA, we can go through a similar program, which is that we measure a bunch of different filament lengths, as shown in the top. We categorize them. That is to say, we separate them by length, and we count how many we get of 0, or 1, 2, 3, 4, etc. So now what we've got is a count of the number of microtubules, or the number of actin filaments, or the number of some other polymer that are of a given length. And then what we can do is we can compute the probabilities by taking that number and dividing by the total number of polymers that we investigate. And the result of that is that we get a probability distribution. Okay, so that's what I have in mind. And going back to this protocol, so we have our probability of interest as our population of interest as a probability distribution. And now what we want to do is we want to work out the ways of moving between the different bins. So let's take a look at that. Let's focus on the bin at L. So these are filaments of length L, and we're asking the question, how does an L become an L plus 1, or how does an L become an L minus 1? So the way an L would become an L minus 1 is because of an off rate. So one of the monomers would fall off. An L minus 1 would become an L by virtue of adding a monomer. And similarly, an L becomes an L plus 1 because of an addition, and an L plus 1 becomes an L by virtue of the loss of a monomer. So as usual, we can write down the flow of probability at each time step. So this is telling us that the probability of having filaments of length L at time t plus delta t is the probability the moment before, and then we can reason out the 4 processes that are exhibited over here, and each one of those corresponds to a particular term, and I can use this to write my differential equation, dpl by dt, and you can see that that's going to be equal to k on pl minus 1 of t plus p k off, pl plus 1 comma t, and then minus a k on of p of l of t, and minus a k off of p of l of t. So that's what our little differential equation looks like. There are an infinity of them in principle because we have filaments of length 1, 2, 3, etc. Although if you were to do this numerically, you would clearly truncate at some high order. Let me also note that if we were doing this on the computer, which we likely will, then the way that you would do this is through this equation, which basically tells you how to step forward in time. So then, given some initial distribution shown over here, we move forward in time and we find the new distribution. Okay, so that's the nature of this chemical master equation protocol, and I just remind you that we already use this in the context of mRNA as I illustrate here. So we've already done this. There's great detail about that. This particular version is for the constitutive promoter. So, interestingly, if I were to be interested in steady state, let's see. Let's see here. Yeah, so if I were to interest myself in steady state, I can bring this down here and paste it, and this thing is going to be equal to 0. So that's basically the essence of the idea. Now, in order to think about our particular case, I need to recall, for different molecular mechanisms, the point is that K on or K off or both can depend on L. And that's the critical point. That's the essence of what we saw in this experiment. We saw that the off rate was proportional to L. So let's now rewrite the equation, our chemical master equation, for this particular scenario. So K on is going to be a constant. So let me actually foreshadow what's going to happen here. So this is L on this axis, and this is the rates on this axis. And here I will put in red, this is K on, and I'm assuming that it is independent of length, and then this is K off, which is a linear function of L, and we see that implies that there is a special point, which is L star. So L star is the steady state length, and we want to find the probability distribution that describes the behavior of this thing. So what does our equation become? It becomes, so let me see, for the case of depolymerizers, our master equation is going to take the form K on of P of L minus 1 comma, and we're in steady state, so I'm going to drop the notation about time, and then I have a plus K off times an L plus 1 times P of L plus 1, and then minus K on P L, and then finally a minus K off L P L. And this all is equal to 0. So that is the case that I claim goes with the sort of most naive interpretation of the Joe Howard Vargas experiment. Could be true that the addition rate is by monomers and the subtraction rate is some larger structure or something like that, and that's a fun alternative to try to think about how one might make this a more sophisticated picture. But this is the one that we have to work with. And I'm going to make a note here for your attention, but I will do the math and thus not force you to try to see the equivalence. And the statement is this is identical. It's not sort of the same, it is identical to the case of constitutive promoter. For mRNA. And there's something about this that I really like and find kind of fun, which is I like the idea that I could have two parts of my laboratory, one of which works on transcription and uses fish experiments and counts mRNAs, and then a second part of my lab might work on microtubules, and in fact those two statements are true about my lab in particular currently. And maybe those people in thinking about microtubules are looking at the dynamics. And what I find really amazing and amusing is that it could be true in the end that those two very different worlds, the people working on microtubules spend a lot of time doing things like purifying proteins, microtubule proteins, tubulin, and they spend time thinking about kinesin motors and so on. And the other side of the group spends time designing DNA. They basically alter the genome. And yet, those very, very distinct things converge on one set of physical and mathematical ideas, and I find a real beauty to that, because that's, in a way, what I have in mind when I think about the unity of the natural world. Okay, so how do we see that this is Poisson? So I'm going to sketch it. I'm not going to go through all the details, but so the sketch of the derivation of Poisson. So when L is equal to 1, then all I have is that K on times P1 should be equal to 2K off times P2. And that tells me that P2 is equal to K on over 2K off times P1, and I suppose I should have actually first done the other case. Let's see. I should have done L equals 0, and there what I would have had was that K on P0 is equal to K off P1, so that tells me that P1 is K on or K off times P0, and now we could do L equals 2, and that's going to imply that P3 is equal to K on over 3 K off P2, which is the same as 1 over 3 factorial, and then K on over K off cubed P0. So I could have said for this one up here, K on over K off quantity squared P0, and etc. So this tells me that P of N, or P of L, is equal to 1 over L factorial, and then I will have K on over K off to the L power times P of 0, and then by normalization, I know that the sum over L is 0 to infinity of P of L has got to be equal to 1, and that I can rewrite as L equals 0 to infinity of 1 over L factorial K on over K off to the L power 0, and this ends up being equal to e to the minus k on over k off, k on over k off to the L power and over L factorial. So this is, as claimed, it's Poisson. I want to remind you something. Poisson, if you have a large average, is a peaked distribution, and that's just worth bearing in mind. So, what we did was we wrote down a rate equation for the growth and shrinkage, and the consequence of that is that we now have a scheme that allows us to compute the probability distributions for all sorts of different realizations of the microscopic mechanisms that control filament length. So the one that we just did is depolymerizers, which is this one. And this distribution is what Poisson looks like when the average starts getting larger and larger and larger. And so, I'm showing you this because as much as I would like to, I'm not going to go into the details of all these different sort of microscopic mechanisms. But I am trying to tell you that in principle, for each and every one of them, you can look at how they work in the language of chemical master equations. And if you want to see a really fun article, you can look at the article by Nishi Mohapatra and Yanni Pandev, and I happen to be on it, but they were the drivers of this whole thing. And it will highlight for you the way that the chemical master equation could be used as a microscope onto mechanisms, signal in the noise, fluctuations, and all of those kinds of things that I've been trying to make a big deal about. So I think that's all I have to say for now about this particular problem.